everyone, my name is Shatabdi. I'm a second year medical student. Welcome to ExamRat. So today we're going to be talking about magnetism. We're going to resume from where we left off in the previous session. So in the last class we talked about how there's a magnetic field produced around a straight current carrying conductor, right? And the direction of the magnetic field depended on the direction of the current flowing, right? So if this was x and this was y, and this was the current flowing from x to y, so by the right hand thumb rule, the current would be going in the clockwise direction, right? And if it was going from y to x, then the magnetic field would be in the anti-clockwise direction. Okay. We also talked about how there's a magnetic field produced in a circular current carrying loop. There we apply the right hand thumb rule in the different portions of the circle to get the accurate magnetic field direction. We also talked about solenoid, right? How it was a copper wire turned n number of times, and when we produced current through it, then it also behaved like a magnet, right? Because it produced a magnetic field, and any magnetic particle, if you placed inside the solenoid, it could turn it into an electromagnet. Now, what was an electromagnet? It was basically a temporary magnet which was formed if you place a magnetic particle inside a solenoid and you supply current through it. So, due to the strong magnetic field produced, it temporarily acts as a magnet, this bar. Let's say it's a soft iron. So so long as the current is supplied through the solenoid, there will be magnetic, the soft iron will behave as though it was a bar magnet having a south and a north pole. As soon as you cut off the supply of the current, it won't be a magnet anymore. So this was our discussion. So today we are going to be talking about the force on a current carrying conductor in a magnetic field. Okay. So we have learned that electric current flowing through a conductor produces magnetic field, just what I discussed. Now, the field so produced exerts a force on the magnet placed in the vicinity of the conductor. So, basically what they are saying is now there's a force also that acts in the magnetic field, okay, which is produced due to the current and the magnetic field both. We'll see how it depends on both. So the French scientist Marie Ampere suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. So basically what they are saying is that if you look at this picture, so what they are saying is that the magnet here, like the horseshoe magnet, is exerting a force because it also has a magnetic field. At the same time, let's say the horseshoe magnet produces a magnetic field M1, and the current carrying conductor, as we know, is producing a field M2. So what they are saying here is that M1 produces a force on M2 and M2 produces an equal and opposite force on M1 by Newton's third law of motion. So what we can say here is that both of them are exerting force on each other due to the strength of their magnetic fields. Now one of them is a current carrying conductor due to which a magnetic field is being produced, and one is a magnet in itself. So what is basically happening is that due to this opposing force, like due to both of them exerting a force on each other, the rod that is placed here through which current is being supplied, it gets displaced. Now, why is it getting displaced? Because you know that a force is being generated as a result of which there is displacement, like the force is causing the displacement. So the displacement of the rod suggests that a force is exerted on the current carrying aluminium rod when it is placed in the magnetic field. It also suggests that the direction of the force is also reversed when the direction of current through the conductor is reversed. Okay. So this we studied in the previous section only, that when we changed the direction of the current, the deflection of the compass used to also change, right? It used to deflect in the opposite direction. So in the same way they are saying now the force is being applied in the opposite direction. Why? Because now the opposing force directions have changed. So how do we calculate the force? Before that, if we so what they are saying here is that when we are changing the direction of the field to vertically downwards by interchanging the two poles of the magnet, it is once again observed that the direction of the force acting on the current carrying rod gets reversed. So in the first case, what they did was they changed the direction of current, right? Displacement changed. Then in the second case, they reverse the pole of the magnet. So now the south pole came here and the north pole went there. So again they saw that the displacement occurred in another direction. Why? Because the direction of force has changed. It shows the direction of the force on the conductor depends upon the direction of current, number one, as well as the direction of the magnetic field. So number one is the direction of the current and number two is the direction of the magnetic field. So experiments have shown that the displacement of the rod is largest when the direction of current is at right angles to the direction of the magnetic field. So imagine that suppose the magnetic field is like this going towards the west, the east, and let's say the current, so this magnetic field is produced by the magnet, mind you, and what I'm saying is that the current here is going this way, like for example, it's a straight current carrying conductor and the current is moving this way. So at this particular position, the force acting on the rod placed here arbitrarily will be the maximum. And why will it be maximum? We are going to learn because of Fleming's left hand rule. So if you see here, according to this rule, when we stretch the thumb, the forefinger and the middle finger of our left hand such that they are mutually perpendicular to each other. So like this, if we stretch them, so the first finger points in the direction of the magnetic field and the second finger in the direction of the current, then the thumb will point in the direction of the force or the motion or the force acting on the conductor. Okay. So basically the thing is that now you can understand why they said that the displacement of the rod is the largest when the direction of the current is at right angles to the direction of the magnetic field, because this is the maximum angle that the three of them can achieve, right? So it can't go beyond 90 degree, because then it turns negative, it starts getting negative, the value. So 90 degree is the maximum, okay, for all the three to make an angle with each other. It's the maximum angle that can be produced. So that is why the displacement of the rod or the force exerted by the magnetic field on the rod is the maximum when the magnetic field is at right angles to the direction of the current. Okay, so this is the Fleming's left hand rule. The thumb is for the motion, the first finger is for the magnetic field, and the second finger is for the direction of the current in the wire. So you can remember it by a mnemonic, is that they have given the thumb word has the word M in it, so M for motion, F first finger for magnetic field, and second finger for direction of current in the wire. Okay. So this is the Fleming's left hand rule, and this is how we calculate the force acting on anything kept in a magnetic field through also where current is being produced by a current carrying conductor. So now since we know Fleming's left hand rule, now since we have understood how a force acts in presence of a magnetic field, and also yeah, So now, since we know that in a magnetic field produced by a magnet, and when current is flowing, there is a force that is being exerted, that there's a force that is being formed, that is being exerted on anything kept in the field of the magnet and the current carrying conductor. Now we will understand its application. So its first application is on an electric motor. An electric motor is a rotating device that converts electrical energy to mechanical energy. Okay, so just 1 second. So it converts electrical energy to mechanical energy. Electrical motor is used as an important component in electric fans, refrigerators, mixers, washing machines, etc. Okay, so electrical energy getting converted to mechanical energy. Now we will understand how it is happening. So if you can see in this picture, so there are two magnets, north pole, south pole. Okay, here basically they are called split rings. So this P here and this Q here. So P and Q are called split rings. I'll tell you about them later. Just for now, understand what they are. Okay. X and Y here, if you see this portion and this portion, X and Y are brushes. Okay. The rest is, I think, more or less simple. This is a coil, okay, placed in the form of a rectangle, and it is attached to the brushes X and Y, and this is a current carrying circuit. Okay, so the device consists of a rectangular coil ABCD of insulated copper wire. The coil is placed between the two poles of a magnetic field such that the arm AB and the CD are perpendicular to the direction of the magnetic field. Okay, so perpendicular to the direction, you have to understand that this is like a 3D picture. So the magnetic field here, so you have to understand that the coil is basically placed like this straight, okay, like vertically, and the magnetic field is like this. So basically it is producing an angle of 90 degree, even if it does not look so in the picture, but imagine it that the angle formed is 90 degree between the field and the placement of the copper wire. The ends of the coil are connected to the two halves of a P and Q of a split ring. Okay, so that's the split rings that I told you. So the ends of the coil are connected to the halves of to the two halves P and Q of a split ring. So they are called split ring because together they form one ring. So they have been split across its center. So now they have become two individual rings P and Q. The inner sides of these halves are insulated and attached to an axle. This is the axle, this gray rod kind of a thing. The external conducting edges of P and Q touch two conducting stationary brushes X and Y. Okay, so here what is happening is that if you look at this picture, so the X and the Y, they are basically connected to the circuit through which current is being supplied, to which current is being supplied, and the brushes and the split rings, they are connected to the coil, okay, to the coil of copper wire. So what's going to happen eventually, I'll tell you. So for now, this is the thing, this is all you have to remember, the split rings and the brushes. So before that, what you have to understand is that when current is flowing and there is a magnetic field also, the magnetic force will produce a torque which will turn the DC motor. So now you can understand that the current is flowing, and as long as the split ring is attached to the brush, so if this is the brush and this is the split ring, so as long as they are in contact with each other, current will flow through it, right? And current is flowing through the split ring means current is also flowing through the coil. And as soon as current is flowing through the coil and there's a magnetic field also, and both are at right angles to each other, you know that maximum amount of force will be generated, which will lead to the displacement of the torque. So now, displacement of the coil. So what will happen is that, if you can look here, is that AB, which was near the North Pole, it will be moved downwards, and CD will be moved upwards. So imagine like a torque is being produced, right? So what is happening is that it is moving like this. So it was like this initially, now it's going like this. AB is going downwards and CD is going upwards. There's a torque being produced. So here also, if you see that due to this torque that is happening, slowly when it has reached a direction, when it is at when it is like CD has completely risen up and AB is completely down, C D A B, what will happen is that the current will the direction of the current will change. Now how will it change is because I told you that since it is a split ring and it is a brush, so what will happen is that when the coil is moving, as in when the coil is moving, same way the split ring and the brush will also move, like it will lose contact and the brush X will go and attach to the split ring Q. So this was P and this was Q. So the brush X will go and attach to split ring Q, and the brush Y will go and attach to split ring Y. So I'll just give you the second image. So here this is Q and P split ring. So the brushes, which are mainly connected to the circuit, don't forget. So now they have interchange. So now this is brush Y and this is brush X. As a result of which, you know that since the polarity has reversed, so the current will also reverse. So at the half position, so if this was the initial position of the coil, so now it has become like this. So at this position, what has happened is that the brushes have changed their position, so the polarity of the current has changed. Now what will happen is that now it will, instead of going like this, it will go like this, because now again the torque will act and push CD downwards and push AB upwards. So the motion will happen something like this. Okay. So this is the whole concept of how the motion of the coil is happening, and due to this constant motion, basically you know that the electrical energy is ultimately getting converted into mechanical energy, right? Because ultimately the torque is being produced and the coil is moving. So this mechanical energy is then um, used in a lot of important components such as electric fans, refrigerator, mixers. So what we have understood here is that the usage of the split rings and the brushes is to alternate the current when the coil has moved halfway. So the coil will never complete a full circle. Okay, so the coil will always be like this. It will always move like this. Okay. So now we come to electromagnetic induction. It is exactly the opposite of what we said right now. It is due to the constant movement of a magnet, there is current production. Or here, mechanical energy is getting converted into electrical energy in the simplest way. So, in electromagnetic, see, the word induction means inducing. So electromagnetic induction. So obviously any normal substance you put inside a copper wire, it will not produce a current. It has to be a magnet. it has to be constantly displaced at a high speed rather, and that will lead to the production of electricity. So how do we understand? So if the magnetic field, again now this is Fleming's right hand rule, so we use the right hand rule for electromagnetic conduction, don't get confused. Fleming's left hand rule is for finding out force, and Fleming's right hand rule is to find the induced current. Induction, so induced current. The things are mostly in the, like, the parameters are mostly same if you consider them, but just the directions always keep changing. So now here what we'll take is that we will take again magnetic field as our first finger, the magnetic field, and our second finger here is the induced current, and the thumb here will give the motion of the conductor. Okay, so if we talk about Fleming's left hand rule here, so wasn't it exactly similar to what we talked about here, right? Thumb was for motion, F was for first finger was for magnetic field, and second finger was for current wires, right? And here what is happening, it is the similar thing, only the first finger is for the magnetic field, the middle finger is for the induced current, and the thumb is for the motion of the conductor. So it's not really difficult to remember because both are the similar things, only in the two cases we are finding out two separate things. Here we are finding out in the Fleming's left hand rule, we used to use it for finding the force exerted, and for the right hand rule we are finding out the induced current. Okay, so now again we have to find its usage, we have to understand its usage. So here what is happening is that here there is an electric generator which uses the principle of electromagnetic induction. Okay, so electric generator means something that generates a form of energy, and here what will it generate? It will generate current, right? So here we know that opposite is happening, that is mechanical energy is getting converted into electrical energy. So here some things are different. Here instead of split rings there are proper rings, right? And brushes, the same thing, so it's the same as it was in electric motor, but instead of split rings there are full rings here. Why are there full rings? Because we'll understand that. So what is happening here is that again you are moving the arm in the so now you are providing the mechanical energy, so you are moving the coil, and when it so happens that the coil has reached the opposite direction, like CD has moved upwards and AB has moved downwards, and it is in a vertical position, it is in a position like this, then what is happening here? There is no question of changing the polarity of the currents, right? So what is happening is that they are taking a full circle around, and basically the next position that they are acquiring is like this. So here it is moving like this, and as a result what is happening is that the polarity of the current is being changed each time this rotation is happening. So also at the same time, when this motion is happening, the galvanometer placed here is deflecting. So when AB was, say, this is the left side. So when AB was the left in the left side and CD was in the right side, so then one rotation happened, the galvanometer deflected in this direction, and then again in the second rotation, again AB came in this direction. So first AB went to the left, so there was, say, a deflection. This is the deflection. Then AB again came to the, sorry, it's the right. Then again AB came to the left direction, so there was a deflection but in the opposite direction. So now each time it is moving, it is constantly deflecting. The galvanometer's arrow is constantly deflecting, which is telling us that there is a current being produced, right? So this is the whole concept, and since there is always constant deflection in opposite two directions, this gives us AC current, alternating currents, okay, because their polarity is constantly being changed, because as you can understand, the coil positions, like the position of the AB and CD coils and also CA and DB respectively, are being changed, right? So that is why alternating currents are being produced. After every half rotation, the polarity of the current in the respective arm changes. Such a current which changes the direction after equal intervals of time is called an alternating current. So this device is called an AC generator. To get a direct current which does not change its direction with time, a splittering type of commutator is used. With this arrangement, one brush is at all times in contact with the arm moving up in the field, while the other is in contact with the arm moving down. So here what you can understand is that here basically as soon as it is going perpendicular, and then it is moving in the opposite direction. So now CD is being connected to B1 and AB is connected to B2. So this is how the crisscross thing is happening, right? They're constantly changing or displacing the position of the coils, because what is happening is that they are sliding through the split rings, right? So if you just take the AB in consideration for now, forget about CD. So what you can see here is that AB was in at first here, then it took a whole slide and then it came here. So now AB is here. So initially it was attached to brush B1, now it is attached to brush B2. That is why the alternating current is being produced, because the polarity is getting changed whenever it is taking a half a rotation. If you have to produce DC current, what you have to do is you have to attach the brush in such a way that as and when the coil hand is moving, so as and when the coil hand is moving, the brush is moving along with it. So then when the coil hand is suppose here, the brush is here. Then the coil hand is moving here and the brush is here. So you have to constantly keep it in contact so that the polarity is not changed. Like when the coil AB has come to this side, then also it is attached to B1 also, then also it is attached to one particular terminal only. So that is how you get the direct current. Otherwise you'll get the alternating current, because the polarity is being reversed. You know that as and when the direction of the current is reversed, the force exerted is reversed, and at the same time when the motion is reversed, again the current induced will be reversed. Most power stations constructed these days produce AC. In India, the AC changes direction after every 1/100 second. That is, the frequency of AC is 50 Hz. An important advantage of AC over DC is the power can be reduced. Actually, here it is not written here. So a large amount of heat energy is basically not produced, is what they are saying. So you can understand that this rotation that is happening, it is happening 1/100th second, at a time interval of 1/100th second. So how fast is it, and how fast the current is being generated? So now we come to domestic electric circuits. As we know that we just discussed how AC current is being used in most of our domestic circuits. So here we receive supply of the electric power through a main supply called mains, right? We know everybody's house have mains. They are either supported through an overhead electric poles or underground or by underground cables. So our circuits are made of in such a way that they have three wires: earth wire, live wire, neutral wire. So one of the wires in this supply, usually with the red insulation cover, mostly it's red in color, is called the live wire or the positive terminal. Another wire with the black insulation is called the neutral wire or the negative. Obviously, to complete a circuit, you have to have two wires, right? So here the current is being flowing and here the current is coming back. In our country, the potential difference between the two is 220 volt. We know that everything has a potential difference of 220 volt. In foreign countries, it is 110 volt. We had discussed it when we talked about the current and when we saw some sums about current. So in India, all mains supply 220 volt of potential difference. So we have found live wire and neutral wire. Find the whole circuit is being complete. So what is the requirement of this earth wire or this green color wire? This is basically so that if in some way there is some extra current here which might cause some problem or cause some short circuit in the appliances, so that extra current basically moves through the earth wire and gets deposited far below the ground. So now you can understand that how every house when it is made and every electric circuit when it is put, there is always an earth connection. What? That is basically a metallic plate that is kept far below the ground where the earth wire is finally connected to, and the extra current that might in any way flow through the live wire gets redirected in this direction and gets absorbed by the metallic plate. At the meter board in the house, these wires pass into the electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. These wires supply electricity to separate the circuits within the house. So you can understand here that everything is kept in parallel because we discussed it in the current chapter also. In case you've missed it, you can go to our YouTube channel and see it. So here, what's happening is that they are saying that after the mains, they go to our houses and there's a meter board in our house from where the segregation happens, like the parallel circuit is produced so that every appliance gets its own current supply. And if by chance there is a short circuit in any one of the appliances, it will not affect the other three appliances. Why? Because it's a parallel circuit, right? So it will never cause a stoppage of current, because if this one goes, so what? It will, the main current is flowing through here, right? So it will flow through here and then it will again flow through here. It just won't flow through here at all. So that's why parallel circuit is very important. So with this, I think the domestic electric circuit is clear, and this brings us to the end of our magnetism chapter. In the next session, we'll go over some basic questions about magnetism, and yeah, then we'll carry on with our next chapter. So thank you for watching.